Okay. Well, hello, everyone. Thank you for joining us today. My name is Daniel Almiral, and I'm so excited you could join us today for this installment of our ISR Insights Speaker Series. For those of you who are unfamiliar with the ISR, we have over 300 faculty, along with ISR's excellent staff, that conduct research that addresses topics such as wealth and inequality, race and racism, politics, public opinion, and a wide range of other topics, including teen drug use, economic behavior, aging, and health. And in addition, and related to today's talk, the ISR also conducts research at the cutting edge of biobehavioral intervention science. And they do this as part of the Data Science for Dynamic Decision-Making Center, or the D3C, at the ISR. The ISR faculty come from almost every school and college on the University of Michigan campus, reflecting the true interdisciplinary nature of our work. The goal of our ISR Insights Speaker Series is to create a forum for disseminating research findings of our faculty at the ISR for the public good. Recordings of these events are posted on the ISR website, and we'll post information on upcoming talks there and on our social media channels. So please check those places to stay connected. About today's talk, I'm very pleased to introduce today's speaker, Walter Dempsey. Walter is an assistant professor of biostatistics and at the D3C at ISR. His research focuses on statistical methods for developing and evaluating optimized digital and mobile health interventions. Today, he's going to discuss the role of sequential decision-making, and that is sequential intervention decision-making, and mobile technologies in order to in health disorder research. As you know, technology presents new opportunities to facilitate behavioral change. Dempsey's work examines the question, or the questions, how do we design treatment plans that leverage mobile technologies for individuals struggling with a variety of health disorders? A couple of housekeeping things. Please note that we are providing live captioning of this event, and you can view those captions by turning on the closed captioning feature on your screen. Also, we will have a Q&A at the end of the presentation. You can submit your questions through the Q&A feature, and we'll do our best to answer them before our time is up. Thank you so much for joining us today. I hope you enjoy the presentation, and I will now turn things over to Walter Dempsey.
Thank you, Danny. It's a pleasure to be here in the speaker series. So as Danny said, my name is Walter Dempsey, and I'll be talking about the role of sequential decision-making in mobile technologies in health disorder research. I set up the talk to be a sequence of sort of 3 vignettes around the questions and topics that my research is touching right now, as well as kind of trying to give you an insight into where the future is, at least as I see it, for this type of research. But before I start with that, let me just, there we go. Let me actually just acknowledge my collaborators both here and at other universities. So I'm very blessed to have great collaborations with Billy and Danny at ISR, as well as Susan Murphy. And then across the UM campus, I have connections with Junka Wu in the Biostat department, and we'll be talking about some of the work I've done with him. Srijan Sen, Mike Dorsch, and Maureen Walton have all examples that I'll be talking about in the sort of context of mobile health intervention development. And I'm very grateful for their sort of collaboration. And then I would be remiss to not mention the 3 students who I have worked with extensively on the topic of mobile health intervention development: Hiroshi, Hannah Vanera, and Madeline Abbott. And so, as I said, this will be sort of this talk I'm hoping to be much more of a tour through current and future directions in mobile health intervention development research, and less on, say, the specific details of a given study. And my goal is to sort of give you a sense of the 3 main gaps and issues that I see arising in mobile health research. So to do that, I think it's best to start with a very high-level definition of what it is: a just-in-time adaptive intervention, which is the basis for a lot of intervention development in mobile health research. Specifically, it's a digital health intervention that adapts intervention delivery to ongoing information about the person. This ongoing information can come from both sensors and self-report. So the best way to think about this is, if I'm an individual in one of these studies, I'm having data collected on me through both self-report, through say a self-report on my phone about my current levels of mood, my current level of stress. And then I also have wearable data that is being collected on me through a wearable device, such as an Apple Watch or a Fitbit. And all of that data is going into a database that is accessible by the sort of scientific team. And what the Jedi does is it takes all of that information on the participant and decides how and when to deliver interventions. And the goal of Jedis and the Jedi sort of research is to provide the most effective intervention option given the individual's context and state. So what we're going to do in this first part, this sort of first vignette, is focus on the Intern health study, which is a study run by Srijan Sen. And here I'm going to talk about a modified version for illustrative purposes. So the Intern health study is a study that's investigating mobile health interventions in stressful work environments to improve behavior and mental health. It's targeting 3 categories of behavior: mood, activity, and sleep. And it's aiming to improve 3 different outcomes: weekly mood, weekly step count, and weekly sleep time. The scientific team decided upon 2 types of interventions that might be provided on any given day: either tips, which are non-database notifications to provide support, or Life Insight, which uses the individual's data in order to produce or sort of improve their behavioral outcomes. The study is for residents in their sort of residential period of their doctoral program. So these are doctors who are residents in their first year. And so this is sort of a high stress work environment in which we're hoping to improve mood, activity, and sleep over this first year. So what's the first gap that I want to talk about today? Well, the first gap is that we want to build an initial Jedi. And the goal is to use prior scientific knowledge, but we still have some trade-offs to think about. The trade-offs are typically that we want to ensure low treatment burden and high engagement while maximizing therapeutic effect. So the scientific team might come together and think through carefully, how are we going to design an initial Jedi that balances between providing interventions when we think are appropriate, but also not providing them too often. So for an example of providing an intervention too often, maybe sending 20 messages a day might be considered sending too many messages. And so you're going to balance the treatment burden with the potential therapeutic effects. And these initial Jedis are designed in order to answer a bunch of scientific questions, which are still sort of, that the scientists may still have. The scientists will have sort of a sequence of 3 more and more complicated questions that they're trying to answer. So the first is, should we even include this Jedi in a future intervention package? Just because you've built an initial Jedi doesn't mean we're confident it's going to have an effect that we actually will see on those outcomes we care about. Even if it is effective, the question is, does that effectiveness change over the course of the study? So in the context of Jedi development, what we often see is that these types of messages trying to promote physical activity, improve mood, or improve sleep might have an initial effect when individuals are highly engaged, but that effect might dissipate over time. And so what we'll want to understand is, how effective are these messages as part of the Jedi, and how does that effect change over time? And then the last question, which is a little bit broad, is how can we improve this initial Jedi? So we're never thinking of a context in which we feel like the Jedi that we've built from our prior scientific knowledge is actually optimal yet. And so we're trying to think of, are there potential tailoring variables or moderators that I have missed that I want to include in a future Jedi? And so we'll talk about how we can answer these 3 scientific questions with a particular study design that the team at the D3 lab has been involved extensively with, which is the Microrandomized Trial. So the Microrandomized Trial takes this initial Jedi, which usually involves a lot of sort of exploratory randomizations, and it builds upon that to sort of learn and answer these scientific questions that I've laid out for you. So in this particular intern health study, the scientific team decided that every single week, individuals would be randomized to either a particular type of notification week or no notification week. So we call these the treatment options. With probability of 4th, you're either going to be on a mood notification week, on an activity notification week, a sleep notification week, or no notification week. We're going to, for the simplicity of this talk, pretend that that notification week type is binary. Either you're going to have a notifications on that week or not, but we can think of more complicated analyses that take into account the weekly level data or the daily level data, which is every single day, you're going to have a half chance of receiving one of these tips or life insights. And with probability half, you will get no notification on that day. What we're going to collect on the individual every single day is both wearable and self-report data. We're going to collect daily mood scores through a self-report, as well as daily step and sleep data through the wearable sensors. These will form what we call the proximal outcomes. These are sort of initial, close to the treatment, so therefore proximal outcomes that we think the treatments are meant to affect. So if I'm thinking of an activity suggestion, this activity notification week is meant to get you to become more physically active on that particular week. And therefore, we're hoping that by sending activity notifications, we'll see an increase in your aggregate average daily step count for that week. The question is whether or not there will be one. And so what we're going to do is once we have all of this data collected, we like to run a series of analyses to answer those scientific questions that I've laid out before. And so for those of you familiar with statistical analyses, I'm going to start by talking about conceptually how these analyses proceed. So conceptually, we can think of what a scientist might want to do is fit a series of more and more complicated models. So a primary analysis model that we might want to fit is just assessing that first question of whether or not there's an effect of these messages on the proximal outcome of interest. So in my analysis I have here, I have YT+1 is indexing or indicating the proximal outcome. It could either be average weekly step count, mood, or sleep. And then I have AT indicating whether or not you received treatment on that week. So it's either a 1 or a 0. And the only thing extra that I've had in this equation that I've shown you here is ZT. So many scientists know that they're going to have variation in their proximal outcome that has nothing to do with treatment. Specifically, if I'm active on one week, I'm likely to be active on the next week, regardless of whether or not I'm providing treatment to that individual. And so we want to include what we call control variables, which are these ZTs, that are summaries of the past and present observations that are related to the outcome. And the idea behind them is we want to use them to reduce noise in the data. So YT+1 is our proximal outcome. There's variation in step count that has nothing to do with the treatment effect. And so if we can think of control variables that are related to the outcome and explain that variability, we can use them to reduce the noise and therefore increase our ability to detect effects of these messages. So in this case, in this primary analysis conceptual model, we think of beta naught as the marginal effect over all observed and unobserved variables of the messages on the proximal outcome. So in the context of those weekly notifications, if I say that I'm going to send you these weekly notifications, beta naught is the average increase or decrease in, say, your average weekly step count, you're going to see by sending you a weekly notifications or not. Of course, the data analyst won't stop here. They'll then move on to secondary analyses, where they'll ask more complicated questions. Specifically, the types of questions we're often really interested in is how does the treatment effect vary with a potential moderator? So what I mean by moderator is a variable that I've collected that I think might impact how treatment is going to impact the proximal outcome. So in this simple example, I have a variable that I'll call ST. And ST is a potential moderator that I'm going to think of as current level of engagement. We'll think of it as a binary variable, 0 if I'm not engaged and 1 if I'm engaged. And you can think of a measurement of engagement as being whether the individual self-reported mood in the past week, or have we not seen a self-reported mood in the last week. So if they're engaged, we might expect to see a larger treatment effect, because the individual is engaged with the mobile health system, and therefore we're expecting that if providing treatment might be more impactful. And so what this secondary analysis will do is test that hypothesis. Specifically, beta naught plus beta 1 will be the effect when the individual is engaged, because ST will be 1, so beta 1 will be on. And otherwise, beta naught will be the effect when the individual is not engaged. And I should mention, they're marginal over all unobserved variables. So with these in hand, these are sort of conceptual models. What our team has focused on doing is translating that sort of scientific conceptual understanding of the treatment effects we're trying to estimate into rigorous statistical estimates and analysis or data analysis methods. So what we've defined for this particular conceptual model is what we call an excursion effect. So this, if you're familiar with sort of an average treatment effect, it's very similar in the sense that at any particular time t, I'm going to look at the effect on average on my proximal outcome given an observed history, and I provide treatment, which is in red here, and comparing that to the average outcome given that same observed history, but I decide not to provide treatment. So this is sort of, if I have a particular observation history, what is the treatment effect that I'm going to see? However, what we know is that we typically want to do analyses marginal over that history, because in the context of mobile health research, that history is quite large. It's all sensor and self-report data that you've collected on the individual in the past period of time. And so if we wanted to build those types of models, that's going to be a quite complicated thing to do. And so instead, what we're focused on is what we call marginal effects, where we average over the history, except for those moderator variables that I indicated in my secondary analysis, this ST. So this ST is what I was talking about before. And what I would just mention is that you'll see this IT equals 1 here. What this IT equals 1 is indicating is an availability indicator. So what availability is in mobile health is the fact that sometimes it's either unethical or not feasible to provide treatment to an individual. So an unethical situation would be if I know an individual is driving a car, I shouldn't provide treatment to that person where the treatment is sending a text message. And a feasibility issue might be that the individual does not currently have Wi-Fi or cell service, and therefore there's just no way of reaching that individual. So in these contexts, we only want to look at treatment effects when the individual was deemed available by the system. And thus we're looking at conditional on ITs equal to 1. And so what we can see is the primary analysis can be written as taking that ST transpose beta, which is the right side in blue, and just treating that as beta naught. While our secondary analysis would having it be that beta naught plus beta 1 ST model that we talked about before. So this sort of summarizes all of our conceptual models in a well-defined estimand. And then the question is, how do we estimate it? And so for the last few years, the D3 lab, Danny, Susan, Billy, and myself have been focused on methods to estimate these types of effect and do inference about this parameter beta. Specifically, what we've derived is a method which is pretty simple, it's interpretable, and specifically it doesn't require much additional work to implement. So it's sort of an off-the-shelf type of method. And the reason these are important is because in terms of communication with the scientific team, we wanted to produce a method that we could talk about with the scientific team and that the scientific team could understand. So what you're seeing here is our proposed what we call weighted-centered least squares method. For those of you who don't want to look at the math, we can just think of this as a way to estimate the beta, but I'm just going to walk you quickly through how this method works. Specifically, what we have is we have a weight out here, and all I'll mention about the weight today, to keep it simple, is that these weights deal with the fact that different individuals at the particular time might be randomized with different probabilities. And so we have to adjust for that. And so we use an idea called inverse probability of treatment weighting. It's very related to that. And so that WT is taking account this fact. The centering is the fact that I took my treatment and I centered it by sort of a randomization probability. What this allows us to do is build models where the control variables, that piece I talked about before, which are the components that are related to the outcome but are unrelated to treatment, they can be used, but, and this is the key point, I don't have to think of this as a complete regression model. So if you're used to looking at regression models, you might have thought the weighted centered least squares looks a lot like a weighted regression model, where I'm taking Y and I'm modeling it given the entire history and the actions. And so you might think that we need the assumption that this entire conditional model holds. But as I mentioned before, HT is quite large. HT is all the data I've collected on the individual up till time t. And so we don't want to make this assumption. And luckily, by doing this centering, we're actually robust to this working model. So we just need to include control variables that we think are related to treatment or related to the outcome, but we don't need that model to be correctly specified in order to have the causal interpretation of our betas that we care about. So what does this mean? This means that because we've done a microrandomized trial where we can use this randomization to really only estimate the causal effect we care about and do inference on those betas that the scientific team has hypotheses about without having to worry about making strong modeling assumptions, which we know are probably not going to hold in most realistic settings. Now, you might say, okay, well, we have our intern health study data, and we could just apply this method off the shelf. And what I'd like to mention for about 5 minutes are some issues that we dealt with over the last year or two with respect to the intern health study and ways that we've sort of extended this base methodology. The weighted centered least squares sort of came out in 2018. And so what we've been working on in the last few years is specific issues around the weighted centered least squares approach in MRTs. So the first issue that I just wanted to mention is that in the residency programs, individuals have residencies in particular hospitals. And so those hospitals cluster residents into different subgroups or different clusters. And what I've done here is I've done specific specialty cluster level analyses where I'm estimating for each of these different clusters a different treatment effect using the weighted centered least squares approach. And then on the bottom, what you have is a summary estimate, which is just estimating using the weighted centered least squares approach, not accounting for the cluster level, which cluster you're a part of. And so what you can see is there's actually some variation in the treatment effect that we're seeing on average across the different clusters. And so what we were concerned with is, can our method handle when you have clustering? So in the context of I ran an MRT, and I'm going to be concerned with cluster level variation in my treatment effect. And what we noticed is that we had coverage probabilities decay as a function of the group size and the sort of treatment heterogeneity variance. And so what you're seeing here is the weighted centered least squares coverage probability, the inference seems to break when I have this treatment effect heterogeneity. And so what we did is we actually derived an extension of this method, which I won't talk about the details here, but I just wanted to mention this is sort of a natural extension of this method to handle cluster level treatment heterogeneity. And so what we end up estimating is we estimated the effects here. I'm showing you the estimates for the intern health study for mood, step, and sleep, where I'm looking at a moderation effect given the past window of time, so the past week's level for mood, step, and sleep respectively. And what you see is very similar behavior across all three, and therefore I'm just going to focus for now on the average step counts. So what this is showing is regardless of which method we ended up using, we're seeing that the average step count is a significant moderator, where if your average step count is high, providing treatment is actually having potentially a harmful effect, while if your average step count is low, providing the treatment is having a positive effect. And therefore, in a future study, what this would inform is we should actually account for this particular tailoring variable. Not only that, but we should use this tailoring variable to say, we might only provide treatments, specifically provide activity notifications, when individuals are having low overall step count. But we might not actually send those types of notifications when an individual has already high step count. So this is one way in which these methods that we've worked on would inform a future Jedi and a future study design. So the challenge number 2 that I wanted to mention is that if I want to go back and look at, what are we doing in an MRT? It's sort of a sequence of little RCTs where I have my history up till time t. I then randomize an individual to treatment or no treatment, and then I observe an outcome. So this is just showing you an RCT, in which if you're familiar, an RCT is a randomized controlled trial in which I have some baseline variables X, a treatment A and an outcome Y. And specifically in the RCT literature, what they've shown is that you can actually do better in terms of being more efficient if you use these covariates in a covariate adjustment to estimate those average treatment effects. So just like in my earlier slides, I care about estimating this beta naught, this average treatment effect, this primary analysis question I had. So in an RCT, this would be an average treatment effect. But what I can do is I can actually center my covariates and include interactions of those centered covariates with treatment. And by doing this, I still retain interpretability of this beta naught as the average treatment effect, and I can actually improve my precision. So why is this important? Well, when you run a study like an MRT, we typically only recruit, say, 100 or so, maybe 200 individuals. And so we want to have different ways to reduce our standard errors as much as possible. And so what covariate adjustment does is it tries to use these X's in a sort of, and uses them in an interesting way in order to increase our precision in our treatment effect estimates. And that's sort of, at the end of the day, a very important thing when we have limited data. So what we ended up doing, and I just wanted to mention it, is in recent work, we actually took this idea of covariate adjustment in RCTs, and we came out with this idea of moderator adjustments in MRTs. So we basically extended this idea to the context of MRTs. And the whole name of the game here is to use additional moderators that we think are actual moderators that might moderate the treatment effect, and use them to increase the precision of our estimates of the beta that we actually care about. So again, all of these techniques are trying to improve this weighted centered least squares method so we can extract as much signal and as much understanding out of microrandomized trial data as possible. Now, the last thing I want to talk about in this context is just that we have sort of what the future might hold. And so what the future might hold is, and I just wanted to mention this before moving on, is that we are really concerned potentially with all of the linearity assumptions that we're making. So something that might come up, a question you might have is, Walter, we have linear models for the control variables, but we know that we might have non-linearity there. We also might have a very non-linear treatment effect. So aren't you concerned that these linearity assumptions are too strong? And so one of the directions that we're taking currently is thinking more carefully about how to use machine learning methods in these settings to estimate these causal effects. And you have to be very, very careful in the context of machine learning methods because they're very good at prediction, but they're not always designed to do causal estimation. And so I'm just going to show you a brief overview of a method where what you can do is, if you want to use machine learning methods, you might use cross-validation, where you take your data set, you'll split it into different folds, and then you'll have a training fold and a testing fold. So in this case, I've done 5-fold cross-validation. And so you use your training folds to maybe estimate that control variable component. And then you'll plug those into the actual weighted centered least squares to estimate the beta separately. And so our sort of future that we're thinking of is a setting in which we can start using machine learning methods to produce better predictions and therefore reduce noise even further while estimating those treatment effects that we talked about before. So again, the name of the game in the slide I'm showing here is I still care about that same beta we just talked about, but I'm really trying to leverage modern machine learning methods in order to improve that precision as much as possible. Okay, so that was sort of the vignette number 1, which is all about how do I build an initial Jedi? I will run a microrandomized trial with that initial Jedi and learn a lot about how to potentially, should I answer those scientific questions that I laid out before? Specifically, should I include this Jedi in a future intervention package? How should I, and what kind of moderators might be actually impacting treatment? And therefore, how should I update this adaptive intervention in a future trial? So the second gap is actually thinking about this more carefully, which is, how do I think about sustainable effectiveness? Which is that we all know that there's a lot of variation, not only at the cluster level I talked about before, but also individual level variation. Specifically, what works for me now might not work for me in the future, and what works for me might not work for a future participant in a future trial. And therefore, we have a challenge, which is we need to think about how to build algorithms that adapt and learn in sort of an ongoing basis as individuals change over time and they have differing needs. So if these aren't accommodated, we might have increased treatment burden, a lack of relevance, and therefore reduced engagement in these mobile health interventions. So the way that we do this and the way we think about this in this context of mobile health research is we think about using artificial intelligence and machine learning to do what we call continual optimization. So in the MRT that I discussed before, the randomization probabilities were fixed. So in the Intern health study, we were thinking of a setting in which those randomization probabilities were fixed, and then I'm going to collect data and I'm going to learn how to improve that policy in a future study. What we can then do is we can then use that as a warm start for a future study. So what I mean by warm start is I might build an initial new Jedi, but what I might need to do is that as individuals experience that Jedi in my next study, I might update that Jedi using algorithms. Specifically, I might change the set or the relative importance of particular tailoring variables. So in the example we talked about on the last slides, what I showed was that average step count on the prior week has an impact, is a moderator for the treatment effect of the activity suggestions on average weekly step count. But that importance might vary over time in a future study, and therefore the algorithm might learn to weight those values differently over time. Not only that, it might learn that the frequency with which we send intervention options needs to change. So it might learn that that probability of sending an intervention being 3/4 compared to 1/4 really needs to change and needs to change to say a half, or it might increase to 80%, 20% or something like that. The overall goal of this continual optimization framing is that we want to have sustained intervention effectiveness. So what I'd like to do is spend a few minutes talking about how we're going to do this in an upcoming trial, which is called Low Salt for Life. And the investigator here is Mike Dorsch. And the goal of this study is to promote low sodium alternatives in individuals with hypertension. So what we know from Dr. Dorsch's prior research is that if we use mobile health technology, when an individual arrives at a grocery store or at a restaurant, and what we do is we suggest low sodium alternatives, there seems to be an effect on reducing overall sodium intake in the near future. And so what we derived was a Jedi in which throughout the day, if you were near a grocery store or restaurant, and that near grocery store or restaurant is GPS driven, so it's using mobile health technology to assess that if statement, we then send a message with 80% probability to promote the use of our app to suggest low salt alternatives. Now, we're going to use this for the first 2 months in our trial, in which during that time we'll collect data and potentially learn that for a given individual, this probability does need to change and this Jedi needs to be updated. Specifically, the way we do continual optimization is we use AI algorithms such as Thompson sampling to change the old Jedi, where we always send with probability 80/20, to change. So in this context here, we might learn to update it so that if you're at a grocery store, we actually change the frequency and increase it because it ends up working more appropriately in grocery stores. But at restaurants, we saw a lower effectiveness of getting you to use the app, and therefore we reduce that probability of sending the message. Why? Because we're worried about treatment burden. So in this context here, we're sort of pushing down the probability at restaurants and increasing the probability at grocery stores. After another 2 months, we might also collect more data and learn more about this individual. And we might learn that not only does it matter what grocery store versus restaurant you're at, but also what situation the Google app, so Google has a way of assessing, your current situation, which is using sort of phone data to figure out, are you in a leisure situation? Are you at home? And things of that nature. So what it might learn is if the situation assigned by Google is leisure, there's even more of an effectiveness of sending these messages than if it just says your situation is other. So in this case, the algorithm will learn to increase the probability of sending messages even more when situation is leisure, but it will decrease the probability when the situation is other. And so here, the goal is to just show you that the old Jedis are being updated to these new Jedis using sort of algorithms based on reinforcement learning. And the trial, sort of the way you should think about it, is that we have a basic Jedi that we run for the first 2 months. And then at week 8, what we're going to do is we're going to assess if we have sufficient data collected on the participant to update that Jedi to those examples that I gave before. And sufficient data will mean that we actually have, the person has gone to the grocery store or restaurant enough that we feel comfortable trying to update and learn a new Jedi on that participant. And so each cohort going through low salt for life is, we're thinking of it in this sort of continued optimization framework, where we're not just using one Jedi and saying, okay, we'll learn after the fact whether or not this was the best thing to do, but also how do we improve it on an ongoing basis within that particular study. Okay, so I have about 10 minutes left. And so what I'd like to do, I'm trying to end by 12:45 to give sufficient time for questions. So I just want to talk about one more area. So what I've talked about so far is I've talked about when I run an MRT, how do I use sort of after the MRT has been run data and extract the most signal possible using different techniques we've developed over the last few years. Specifically, how do I figure out what moderators matter? So should I include the intervention and what moderators matter for a future trial? And then the second gap, what I was talking about is, okay, I might use that data for a warm start policy, but I know that individuals vary a lot in my particular population. And so I can't use a one size fits all strategy. So I'll use reinforcement learning to improve those policies over time. And what the third gap is you might say, okay, even if we're learning over time how to improve this mobile health intervention, how do you know it's enough? So specifically, we might be concerned that digital component, even with an optimized Jedi, might not be sufficient for a particular individual. And so we might want to integrate digital interventions with human delivered interventions, where the human support can combat things like disengagement with the digital services, while the digital components can sort of extend the therapeutic contact beyond the clinic. So the third gap is trying to figure out how do we integrate digital components with human delivered or human support. And specifically, the gap is we don't know how best to sequence and adapt these two together. So what I've talked about for the last about 40 minutes or so is this just-in-time adaptive interventions, and where these are digital components that are sort of varying quickly over time. So there's fast timescale adaptation, and the experimental design is MRTs. But if I'm thinking about human-delivered interventions, I'm thinking of more traditional adaptive interventions, which vary on a much slower timescale. Specifically, I might vary them, say, every 8 weeks or so, I might come in and assess non-response to a digital intervention, and then decide what to do on those types of individuals. And this is basically what we think of as a SMART, or a sequential multiple assignment randomized trial, which the D3 lab has had expertise in for a very long time. What an adaptive intervention is, and this is an example coming out of substance use prevention in adolescents visiting the ED, is it's just a sequence of decision rules deciding what to do, but at this slower time scale. So in this example here, I'm thinking of an emergency department visit by an individual, at which point we're going to provide one session to sort of reduce risk and reduce risk of the individual and increase resilience, as well as provide that individual, that adolescent, with a digital intervention that's going to provide messages throughout the day to try and increase the resilience sort of outside the context of the ED. At week 4, this adaptive intervention will assess response and non-response. And if they're a responder, then I'm going to just continue with the digital intervention. But for non-responders, I might increase by including remote health coaching. But of course, with these types of adaptive interventions, I also have questions I want to ask and answer. And specifically, I might be concerned that the digital intervention plus one session may not be enough. And then I might be worried that remote health coaching might not be enough for non-responders. So when I have questions about adaptive interventions, So when I have questions about just-in-time adaptive interventions, I use microrandomized trials. When I have questions about adaptive interventions, I use sequential multiple assignment randomized trials, or SMARTs. So these are experimental designs that have been around for a while to understand and answer questions about adaptive interventions. And specifically, what we do is we have sort of sequential randomization, but here, as opposed to in a microrandomized trial, it's typically 2 to 3 randomization time points. So in this context here, the SMART will, at baseline, randomize individuals to just a session and digital intervention, or a session digital intervention and the remote health coach. After 4 weeks, we're going to assess response status. If they're non-responders, we're either going to continue or step up. And so what you can see in this particular example, excuse me, is that we have randomization occurring at 2 time points, and these are these human-delivered interventions matched with digital interventions. But specifically, these digital interventions, we might be learning in the same way as I had talked about before. And specifically, these digital interventions, we might want to learn how to do them as best as possible. So we might have, in the same way I talked about before, an initial Jedi in which we have an understanding of how maybe we're going to start off, but we want to learn how to do better. And so in this context, we might have daily messages, but we might randomize the individual to either receive a message or no message on every given day, rather than just send it with probability 1. And what this will allow us to do is answer questions about that digital component. And so what are we really doing? Well, when we do this, if we think about it, we have a sequential multiple assignment randomized trial, and we have an MRT running on that particular digital component. And so what I'm trying to do, the kind of questions I'm trying to answer, are about adaptive interventions when I'm trying to adapt at multiple timescales. So I'm trying to adapt the digital component on a day-to-day basis, and I'm trying to adapt the human-delivered components on a month-to-month basis. And not only am I trying to do them separately, but I'm trying to do that in tandem. And so the way we think about this as an intervention framework is it's sort of a marriage of your traditional adaptive interventions with just-in-time adaptive interventions. And we call these multimodal adaptive interventions. And specifically, they are adaptive intervention plus Jedi equals a MADI. And these are intervention designs where we're operationalizing them as the integration of these adaptive interventions and Jedis. And just like we have an MRT and a SMART, we'll have a hybrid design to answer questions about that integration. That hybrid design in this particular example is simply the addition of a SMART with an embedded MRT. And in this context, it allows us to answer questions not only about how to improve the Jedi and not only how to improve the adaptive intervention, but also how to jointly improve them. So for example, we might want to ask, okay, what is the effect of these daily messages? So what is the effect of the daily messages over time under different adaptive interventions? So we can see here that we're actually asking a question about the Jedi, but in the context of a particular adaptive intervention, which is very different than thinking about moderators. And so we are starting to think carefully about how do we analyze data coming from a hybrid design, and how do we take advantage of this integrated experimental design to learn optimal policies quicker and at these 2 timescales. Okay. So just to highlight one last time, these hybrid designs now have 2 levels of randomization. In the adaptive intervention, I have randomization at 2 levels, which is week 1 and week 4. But in the MRT component, I'm having randomization every single day. And so we're having multi-scale randomizations happening in sort of a factorial design structure. Okay, so it's 12:45, and I'd like to make sure I have time for questions. But I want to stop and just sort of say what I hoped you learned today. So what I hoped you learned today is sort of 4 things. And specifically, the main overarching goal is for us to start thinking of these studies less as one-offs, where I run a microrandomized trial and I think I can build an optimal Jedi, and then I just deploy that optimal Jedi in a future study. But really, really start thinking about these micro-randomized trials and hybrid designs in a much more continual optimization mindset. So we'll run an MRT, we'll build a warm start policy, and then we'll learn on that individual over time using reinforcement learning techniques, and we'll continue to do that until we sort of think of the algorithm as being well-defined and sort of working very well, and then and only then we will then deploy it. But even when we deploy it as part of an RCT comparison, we're still learning on it, the individual over time. So this continual optimization mindset is really what I'm trying to emphasize in my talk today. The first gap that I mentioned is this growing set of mobile health methods for understanding time-varying causal effects. The goal of all of these methods is to make them off the shelf as much as possible, accessible and easy to understand. So in every single context that I talked about, we had the beta came from that conceptual model. And if there's a part that's hard to understand, like in the machine learning example I gave before, we want that to be as much under the hood as possible. The second gap I talked about was personalization via reinforcement learning. So specifically, we know that even if we run one of these MRTs and learn a lot about what moderators matter, we know that individuals vary both over time, but across different individuals. And so we want to think about how do we carefully use reinforcement learning to improve and personalize the policy for that particular individual. There are a lot of issues with doing that. Specifically, we are often a low signal to noise setting with these MRTs where there's a lot of variation in your proximal outcomes that have nothing to do with the treatment effect. So how do we balance learning on the individual with this low signal to noise ratio issue? And the ways that we've done this in the context of our problems was we're thinking a lot about how to do sort of intermittent updates rather than update every single time. Say in the example of low salt for life, we're updating every 2 months. And we also might start considering how to pool across people to do better by using sort of additional information on other people. The last thing I talked about, and the last gap that I think is really critical for digital intervention development, is integration with human-delivered components. We really don't want to think of digital interventions as components or as packages by themselves. The digital intervention is a component in an overall intervention package that we're going to deploy. And specifically, we're really thinking of them as potentially scalable solutions for parts of our population, but they might not be sufficient for everybody. And so that naturally led to questions about how to integrate digital interventions with more traditional adaptive interventions, and specifically the synthesis of SMART and MRT designs and methods. Okay, and with that I'll end. So I wanted to thank everyone for listening. I don't want you to think that this is a sort of we are done type talk. What I really want you to think of as sort of there's lots of work ahead and it's sort of an exciting time to be in this field. And hopefully I've sort of stirred your interest enough to ask questions after the talk. But if you have more questions beyond this talk, please feel free to email me. I'm more than happy to kind of chat offline as well. Okay, so I think I'm asking myself these questions, so you'll have to bear with me as I read through them as well. So I see 2 questions already in the chat, and I'll start with those. And then I'll sort of see if there's any other ones that pop up. So the first question I see is, I was wondering about the already high step count individuals, so I'm glad that you mentioned them in your findings. I would like to know if you may consider in the future giving those individual notifications focus more on mindfulness or relaxation strategies. So this question is really, really important. So let me go back to that set of my slides. So the question, just to repeat it, is right now in this Jedi, this sort of initial Jedi, we're not taking into account any of these moderators. But the point that I raised is in the methods that we've developed, what we noticed is that for people who already have high step count, we're actually seeing that there's a sort of a deleterious effect. And so therefore I mentioned we might have a future study in which we use the moderator of we will only send activity notifications if you have low step count. And to the point that, and I might have lost the name, Dale is the one who raised this question, and it's very important. When I say that we're potentially not going to send you activity notifications, that doesn't mean we won't consider other types of notifications. So in the context of these types of studies, what this means is we might consider alternative, more preventative type messages around things like, when Dale mentions, mindfulness. So we might consider it as reducing the probability of sending an activity notification, but still considering other intervention options, such as these mindfulness or relaxation strategies. So Dale, this is a great question and a great point, which is when you have these multi-component interventions with multiple intervention options, we really don't want to have high burden. So we don't want to send too many interventions on a given day. So often the trade-off is, which intervention component am I triggering now? So what this tells us is I should turn off the activity suggestions in this particular context. And that gives me more ability to turn on other intervention components in that context. That's a great question. Sylvia asks, what to do if we only have observational data? In your opinion, what would be the most important challenges to address in this case to build a reliable Jedi? So this is a great question. So I will say two things about it. So luckily for me, I have, in most of my trials, I'm the experimenter. So I have control. There we go. Where is that slide? So I am the experimenter, and so I know my randomization probability. So the reason I show these die in the top right corner is because I know ahead of time with what probability did I send this message. And because I get to control things, I can actually have all of this robustness to model misspecification that I mentioned on this slide here. So to Sylvia's question, Sylvia asks, what do I do if I have observational data? In that context, just to make it clear to everyone what the issue would be, it would be a setting in which I am given data like the intern health study, but I don't know how the individuals were randomized over time. So I don't know the randomization probabilities. So in that context, what we're really concerned with is that there might be I might be misspecifying these weights, and therefore I might not be robust to it. So this method that we talked about, Sylvia, Sylvia is a method that we consider somewhat doubly robust, which is if you get, there we go, if you get the randomization probabilities correctly estimated, or you get this working model correctly estimated, then you can be sort of more confident that your inference will be correct, in the sense that your betas will have correct coverage and you'll have consistent estimators of the true beta. Now, the biggest concern with observational data in this setting is twofold. First, if the randomization probabilities are really complicated models of the past history in observational data, so if you think, for example, that the probability of treatment depends on some really complicated model of the past history, or you're worried that your outcome is also a very complicated model of that past history, then you're really concerned with using these linear models that I talked about today. You're really worried that, well, what if I get this model wrong? What can happen? So first off, you'll still reduce bias, and in a lot of observational studies, when you use these kind of doubly robust approaches, even if you get the model wrong, you're sort of reducing bias. But the other reason I wanted to mention these machine learning methods is that they're really targeted towards those settings you talked about, where you're really concerned with model misspecification, and so you want to use machine learning methods to do a better job. And so my kind of recommendation at a high level would be you have to more carefully think about these questions of modeling and model specification, and carefully modeling the treatment probabilities. Even if you do that, I would still recommend running if you can, a clinical trial after that, but that doesn't mean you can't use that data in a similar way to inform a future trial. And so that's sort of my recommendation, is think more carefully about how to build these models. And then even if I do so, I still want to run a trial at the end of the day, if possible, because randomization is it makes everything so much more robust. And so the biggest slide from my perspective is by randomizing, we have much, much more robustness to a lot of the specification issues that can happen in observational data. But great question. Okay, it is 12:55. So I see one more question, and let me just get to it. So the last question was on, let me get there, sort of this modeling, how does this work in this context? So the question was, so you say you have a basic Jedi and an updated Jedi, how does that actually happen in practice? I saw the word cohort, but I didn't see how you used it. Okay, so yeah, so I have about 4 minutes, so I think this will be my last question. The way that this works, so let me break it down a little bit more carefully, is when I say basic Jedi on the low salt for life, I am thinking of this simple rule around, similar to the intern health study, we have some basic Jedi that is randomizing people when they get to a grocery store or restaurant with probability 80% of receiving a message. So we think it's good to send the messages, which is why that probability is high, but we still want to learn, which is why we made the randomization probability not equal to 1. So what does that give us? That gives us 8 weeks worth of data. Why did we wait 8 weeks? So the first reason we waited 8 weeks is because we're very concerned that there's not going to be sufficient data if we update after a week. People don't go to the grocery store more than, well, the average person doesn't go to the grocery store more than 1 or 2 times a week, and you might have a lot of variation in when a particular individual goes to restaurants. By waiting 8 weeks, we hope to have enough data to update that Jedi. So the first idea is the signal to noise ratio issue of waiting 8 weeks, we hope to have sufficient data. And so we have this rule around only when we have sufficient data will we update our Jedi. And the way we do that update is, you can think of it as running a regression model, but it's a Bayesian version where we use the posterior distributions, sort of the uncertainty in that model, to do further exploration. So what the model will learn is how different moderators that we've picked out impact the treatment effect, but those parameters will have uncertainty. And the way that these updated Jedis work, these Thompson sampling algorithms work, is they use that uncertainty in the algorithm for future treatment decisions. The only other part that your question mentioned is the cohort issue. So in your first, so if we're thinking of a traditional trial, we're sort of recruit on an ongoing basis, right? We don't have all 1,000 or 100 people just arrive at the beginning of your study and you can just pool everyone. So when I talked about partial pooling, right, in your model, you might want to pool across people, but if people are starting on an ongoing basis, it's really hard to figure out how to pool when people are entering and exiting the study all the time. And so this is both an engineering issue as well as a recruitment issue. And so the way that we solve this is we're thinking of more cohorts where the first 50 people, we're only going to use the data on that particular individual in that updated Jedi. But in the next set of people, so in the subsequent 50, all those first 50 people will probably be done with their first 2 months. So that first cohort will be used as a sort of to partially pool with your individual data. So if I, Walter, arrive at 8 weeks and I'm in the second cohort, we're going to use the first cohort's data to help us learn more about me, Walter. So that updated Jedi, if I look a lot like, say, 10 people in the prior data, so in the prior cohort, there's 10 people who look a lot like me, and then I can just pool all of their data together and build a better Jedi because I have more data on that type of person. So sufficient data becomes cohort specific, where as we go cohort to cohort, we have more and more data on other people, and we get to use that to have a more updated Jedi. And so for people late in the study, we're always going to be able to update as long as there's people who look like them in the original previous cohorts. Okay. I think that's all the questions, and it is 5 seconds to 1. So I think this is where I will end, and I want to thank everyone for sticking around and listening. And yeah, no, it's been a great opportunity to sort of talk. And again, as I said, if you have questions for me, either on the statistical side or the design side, or even the substantive side, I'm more than happy to discuss it offline. And I will end by going to my final slide, just so you have my email sitting there in case you're interested. Okay, thanks everybody. and have a good rest of your week.